Now we're going to calculate the magnetic incident field from the electric incident field. The important thing, first of all, is the picture. There's the k vector unit vector in the direction of k, n hat k. There's the direction of the vibration, the polarization of the electric field, n hat e. We know that H has to have a perpendicular direction to those two, so it's sticking out of the board. NH is in which direction? Well, I think you can see that from the fact that X is down and Z is down, that if I take the cross product of K, N hat K, and N hat E, it's going to come out of the board, which is in the negative Y hat direction. So it should go like the direction of this unit vector, it's actually equal to negative J hat. It's coming out that way. That's because otherwise we'd have a left-handed coordinate system. X, Y would be into the board and Z up, but it's coming out. So we have N hat H is minus J. That's the directions. Now we know how the directions of K and H and E vectors are related. We now need to finally be able to compute the H amplitudes. So let's look at the fields. Here's EI is equal to the vector amplitude times the plane wave solution. H is also sitting on the same plane wave, and it has a vector amplitude, H1 plus. Now, we also know that Ki is equal to a unit vector in the k direction times omega square root mu1 epsilon 1. We're in the upper medium. We know from our work on the exams and in class that the amplitudes of such waves are related by Ki cross E1 vector amplitude is equal to omega mu1 times vector amplitude of H. Now what we do is we write the vector amplitudes in this form, so we substitute in for E like this, and there it is, and that's a scalar, curly E1, 0. We also write the vector amplitude for H as the unit vector for H times the amplitude H1, 0. Now, we know that Nk cross Ne is N hat H. These are all unit vectors. And now I need to, so we know that the vectorial part of this equation is satisfied. Let's just do the scalar piece. So the omegas cancel out here. And in terms of the scalars, we can divide mu1 epsilon 1 in there, and so we can see that the scalar value epsilon 1 is equal to mu1 divided by square root of mu1, so that leaves me a mu1 in the top, and this epsilon 1 square rooted will be in the bottom. Now, units. The units of the amplitude, electric field, volts per meter, amps per meter. Therefore, this has to have the units of impedance. And that is what we call the intrinsic impedance, the impedance of the material, just like in circuits. And we call that eta. So I'll be sure to make the tail long enough so we don't confuse it with index of refraction. Eta 1 is equal to this. Now, it's clear that since this is eta 1, I can simply solve for the scalar value of the amplitude of the incident H field, and I get that. If you recall the previous figures, the H's are always going in the same direction, so they're all going to be basically scaled values of the amplitude of the electric field divided by the appropriate intrinsic impedance. We can put it all together and we can summarize it, but before we do that, let's do this as an exercise. Let's see how we can match all the E's and H's appropriately at the boundary and get the result that we want. What are the dynamics associated with reflection and transmission?